Okay, there's a few more things I wanted to finish up on the atomic theory of the electron and their atoms. So I'm going to pick up with where we left off. We were talking about if we place hydrogen gas in a magnetic field. So so the general idea, let's backtrack a second. So we said that if we take the Schrodinger solution psi of n, l, and m, which were the quantum numbers of the wave function r, theta, and phi, that there were the energy levels only depend on the principal quantum number n. So this was called the principal quantum number. This is called the orbital quantum number, and this, of course, was m sub l. And the energy E sub n was minus 13.6 eV divided by n squared. And it depends only on n. Now, we can actually show under certain conditions that that the energy levels can depend on can or will depend on L, or we should say m sub L, if placed in a magnetic field. So if the atoms are in a B field, right? And so we're starting to look at what the effects of that were. That's an important consideration because, you know, if these quantum numbers are real, then there should be real effects that are due only to angular momentum, and in a way that's predicted by the Schrodinger equation and the energy levels that we can observe. And you'll recall that the way we observe these energy levels is if there's a transition between two energies, I get a photon emission, which is equal to hc over lambda, which was equal to the energy levels of, for example, a transition from the nth energy level to the nth energy level, right? So I can calculate what these are, and the way I observe that the energy levels are real is that there are light of a given wavelength that is consistent with this equation. And when I observe that, then I do find that I get a direct correlation, and that these energy levels do depend on the quantum numbers as we've shown. Now we're going to look and see, or as was done by Zeeman, that the observation of what's now called the Zeeman effect is that we do get these, what we call the splitting of the energy levels. So not only does it depend on n, but it's going to depend on the third quantum number m sub l, and we'll get to this in just a second. So let's set up the physical basis of the measurement. The idea was that if I place the atom in a magnetic field, and let's see if I can draw the atom here. So let's say, for example, that I have the atom, the electron is moving about the nucleus, and it has a certain momentum or velocity v in this direction, or momentum p, and this has a certain radius r to the radius of the orbit. Then I find that I can get L is equal to r cross p, and these values are quantized, and in particular the magnitude of L, according to the Schrodinger equation, is the square root of L times L plus 1 times h bar, right? And so this is what we had for the angular momentum. Yes. Sorry. Okay. Thought I heard you. No. Was there a question back there? No. Okay. Sorry. I must have hit a chair and thought it was somebody speaking. Sorry. Happens to me all the time. Let's see. So what do we have? Okay. This is the general picture, and because the z component of the angular momentum is quantized, then remember we can draw this picture that that first of all the L vector, which is r cross p going this way. So now I'm going to actually try to draw an angular momentum vector. I'm going to have to take this one out too. Sorry about that. But the angular momentum vector is perpendicular to the plane of the orbit. So this will be the inclined plane of the orbit, and this is the angle of r cross p. So furthermore, that the L, or I should say the angular momentum in the z component, was quantized in terms of allowed vectors or orientations, and that, for example, if I have L equals 2, then I can have m sub L equal to minus 2, and its value of the its value m sub L minus 2. This is m sub L equal to minus 1, and the quantized values will be, for example, 2h bar, and this is 0, and this will be minus 2h bar, and of course this will be plus 1h bar, etc. So the z component has been quantized. Okay, so that's a little bit of the backdrop, and then of course we have the magnetic field itself, where the magnetic field is in the direction vertically. This is the magnetic field. This is the north pole of the magnet. This is the south pole. So we place the atom in a magnetic field. And let's see what else would happen. So now this is the scenario that we have, and we want to look at the energy levels that are accessible or possible for the electron. And because the electron has orbital angular momentum, L, then, and it has charge, so we have a charge on here, that this angular momentum is going to lead to what's called the magnetic dipole moment, mu. Right? I was going to make copies of that, but for those of you that may not remember this, this is in chapter 30, and I believe that the equation was 30.48, which is the equation for magnetic potential energy of a current loop. I'll try to verify that in just a second. So this is called the magnetic dipole moment. Magnetic dipole moment. And the basic idea of the magnetic dipole moment is that if I place a current loop, which is what we have here, so a current loop has, and this of course would be from Maxwell's equations, right? This is just some current I in a closed loop. And it is placed in a magnetic field, B, then there will be a torque on the rotation axis. There will be a torque that will cause a spinning of the loop of the current. So this I is connected to a voltage source, right? So I generate a current through a wire. Then there will be a torque on this loop that will tend to orient the normal to the area parallel to the magnetic field. So the way we define this is that there is a unit of potential energy, which is equal to minus mu dotted into the magnetic field, B. And this is what we call the magnetic dipole potential. And basically it acts just like you would, as I said earlier, that if I had, for example, a bar magnet that was in a magnetic field, that it would in fact spin the bar magnet in such a direction so that, for example, with the magnetic dipole moment, B is operating this way. With the magnetic dipole moment, let's say in this direction right here, that it will in fact align the magnetic field so that the mu dot B becomes a minimum, or minus mu dot B becomes a minimum. That is to say that the dipole field of the external magnet will tend to torque the magnetic dipole of the miniature dipole magnet so that it is parallel. And when it's parallel, it has minimum potential energy because north and south are perfectly aligned, and so it is down here. So this quantity represents the magnetic potential energy of a current loop. Okay. Now, because of the fact that a current loop looks very much like the magnetic field of a bar magnet, we associate a magnetic dipole moment with the current loop. So in your earlier 273 course, you can look up and find that mu is equal to the current in the loop times the area. And area is a vector. And the vector area is normal to the surface of the defined by the loop of current. Okay? So there's a magnetic dipole moment that's equal to the current times the area. Okay. And this represents the interaction area, the interaction potential energy of the dipole moment that is generated by the current, in this case the electron, moving around in an orbit, and we'll treat it semi-classically to get the effect of what's actually going on. Let's see. So yeah. So how do we relate angular momentum to magnetic dipole moment? So we're going to use this in the energy equation that we're going to add this term on to the energy that is already existing as a result of the Coulomb barrier. So now we can say that E sub n is equal to minus 13.6 eV divided by n squared plus the potential energy of the dipole moment interacting in external magnetic field. And so this becomes minus mu dot. Okay. Now, we said earlier that the magnetic field B is going to define the z-axis for us. So I can say right away that B is equal to B sub z. This is in fact what how we define an axis for the atomic system. And so I can replace this with the z component, this dot product of the z component times B. And that simply becomes a simple scalar product. So the problem now is we want to calculate, does this orbital angular momentum produce any measurable results in the energy levels, and therefore in the lines of the frequencies or the wavelengths that can be observed? And we're sort of heading towards that path, and I'm trying to, that's sort of the general direction that we're going. Last time we derived an equation which said that given that this equation is true, and I can also write that the current is now the one electron charge divided by the classical period of revolution, where tau is the time for one orbit. So tau is equal to the time for one classical electron orbit. Okay? And so that then gives me charge divided by time times the area, and the area is pi r squared. So we take pi r squared as being the area of the electron orbit. So current times the area gives us the magnetic dipole moment, and so now what I can do is I need to do one more simplification. This period tau can be written in terms of the orbital angular momentum, or the orbital frequency, And that is given by the period of time is the 2 pi r, the circumference divided by the velocity. But r over v is also, or v over r is the angular velocity. V over r is omega. So doing the substitution then, I get that mu, so I get that tau is equal, this is equal to 2 pi over omega. So 2 pi over omega. Now I can eliminate tau from these two equations, and I get that mu is equal to minus e over 2 times omega r squared. Right? So this is the expression for the magnetic dipole moment. Furthermore, I have that angular momentum can be equal to, written as the moment of inertia, which is mr squared, times omega. Okay? So now I can put these two together and eliminate omega r squared, and I get that that mu is equal to minus 1/2 e over m times the angular momentum L. Okay? So we now have the relation that they're by virtue of a charged particle moving in a circular orbit with angular momentum, it creates a dipole moment, and that dipole moment interacts with a magnetic field with a potential energy of mu times dot b, or in this case mu sub z times b. Okay. So now if we want, now we begin to see that I just need to evaluate mu and replace the value of mu or mu sub z in this equation. So I'm going to get that the interaction potential energy U is equal to minus mu dot b. So this is equal to minus 1/2 E over m times L sub z. That would be mu sub z times the magnetic field B, and this would be equal to replacing the value of L sub z, which are quantized values of angular momentum. This becomes mass times m sub L h bar. So there's my z component of angular momentum times B. Right? And if I evaluate this constant out front, which is everything except these two terms, then I can evaluate this numerically because I know what the mass of the electron is. This is 5.5 times 10 to the minus 5th eV per Tesla, right? Times m sub L times B. Okay? So I now have a potential energy that is due to the angular momentum. Let me close this door. I'll be right back. So we now have a potential energy that is due to the interaction of a current loop, which is my electron moving around in relation to a externally applied magnetic field. And I can evaluate how strong a potential or how much energy that produces. So now I'm in a position where I can write down what these what in fact I expect to happen. I can write down the potential energy diagram for a couple cases. Let me choose a particularly simple case. Let's suppose that I have the ground state energy with E1 equal to minus 13.6 eV. Right? And for this particular case, we know that L is equal to 0. So there's no orbital angular momentum. So there's not going to be any interaction with an external magnetic field. There's no momentum. There's no magnetic dipole moment that's generated by the circular charge. Therefore, the additional term to add on here is 0. There's no value. Mu is equal to 0 for the L equals 0. Right? For L equals 0, m sub L has to be equal to 0. And if m sub L is equal to 0, then this potential energy is 0. Okay, so the magnetic field has no effect. So this will be over here. I have to rewrite this a little bit differently now. So here we'll say no field off, and over here we'll say B field off. And on this side of the column over here, we'll say B field on. B field on. Okay. So here, now let's go to the second energy level. The second energy level is going to be at minus 3.4 eV. Right? That's 13.6 divided by 4. 4, right? Now, if I turn on this magnetic field, I now have 3 energy levels available. One for m sub L equal to +1. One for m sub L. This is m sub L. The top one is m sub L equal +1. The bottom one is m sub L equal -1. And this one, of course, this energy level stays constant. So now what happens is that before, when there is no field turned on, I excite the atom to n equals 2 by, for example, collisions with electron. Then this one can de-excite, come back down, and it gives off an energy of 10.2 eV. Okay? So that's a 10.2 eV photon. That's the negative 3.4 minus a negative 13.6 is the energy difference. It gives off a photon. That's the energy of the photon that's given off. And voila, that's what I have. Okay? Now, let's suppose that we put on a magnetic field of B equal to 2 Tesla. 2 Tesla is a fairly strong field, but on the other hand, it's not totally unreasonable. It's certainly a field that we can achieve with moderate difficulty. So this now becomes the field on. So what is happening to the splitting of the energy levels? Well, with m sub L equals 0, right? There's no change in the energy, right? Because m sub L equals 0, then this term is 0, and then you're just left with 13.6 divided by this is n equals 2. Right? And by the way, I'm looking particularly in this case of L equals 1, right? This one is L equals 1. Which, by the way, I should probably put over here, because this will make it more consistent. Let me try to do it in a more easier way. And let me try to replace this mu is equal to minus 1/2 E over M times, times L. And this is going to be L equals 0. And this one is going to be L equals 1. Okay. And this one, with field off, gives off an energy of the photon equal to 10.2 electron volts. Right? That's the difference in these two energy levels. Now, if I turn the magnetic field on, then this energy photon will still be the same, but now I've got 2 more energy photons. I've got one that can go from here, and I can have one that goes down to here. Right? So, how much is that going to perturb it? Well, I'm either going to add a certain amount of energy onto my unperturbed level, or I'm going to subtract the same amount, because m sub L equals 1 and m sub L equals minus 1 only changes the sign of the interaction and nothing else. So let's calculate this. So now I want to look at the energy levels for L equals 1, m sub L equal to +1, and m sub L equal to -1. Okay, so for those two cases, I'm going to get that the interaction potential is equal to, by the way, notice that because I've chosen E, we've said before, is always greater than 0 in my notation. So when I write E, what I really mean is the absolute value of E. That's the charge of the electron. Right? That's what we mean there. And also because there is a minus sign here between the mu and L, right? Because of the fact that the charge of the electron is negative, I explicitly put that in with a minus sign so that the magnetic moment is opposite the direction of the angular momentum. Unless I'm talking about protons, for example. Protons are positively charged, right? So if they're positively charged, then the magnetic moment will be in the same direction as L. But because E is negatively charged, then current goes opposite the direction. And I keep that minus sign in here, and that gives me that. But the potential energy is minus mu dot B. So I have a minus sign here and a minus sign here. So when I add these two together, I get that this is equal to minus the total energy now, which is going to be a function of both the quantum number n and the orbital angular momentum m sub l, minus 13.6 eV divided by n squared. And this is going to be plus 1/2 E over m times h bar times m sub l times b. Okay? And m sub l can be equal to +1 or -1. It can be either one of those. It can be +1 or -1. So I just evaluate this, and I've already evaluated these explicitly in terms of energy units. The value of this quantity is 5.5 10 to the minus 5 eV per Tesla. So I only have to multiply by Tesla to get the total EV. So I'm going to evaluate this now for B equal to 2 Tesla. And I now get that this is, this can be 1.1 times 10 to the minus 4, or 1.1, or minus 1.1, or minus 1.1 times 10 to the minus 4, EV, right? So now what that tells me is that these three energy levels are going to be able now to produce 3 different photon energies when I turn on the magnetic field. And that's what's observed. That he might have gotten a Nobel Prize. I'm not sure about Zeeman, but they were coming so rapidly. But when you turn on the magnetic field, I get one energy photon of 10.2. When I turn off the magnetic field, I'm sorry, but when I turn the magnetic field on, then I can now get the energy of the photon for the n equals 2 to the n equals 1 transition. So this is, the photon energy, gamma, is going to be equal to 10.2, and then there will be 10.2.011, and there will be and then I'm going to subtract, so I'll get 10.100099 EV, right? And these may look like very small differences, and in fact they will. Now let me make sure I did the subtraction correctly, because it's a little bit hard to do this. Here I've clearly added 1.1 times, I think I've done that right. Then I get 3 energies, and it's observable. It's observable. So these energies are observed. So with field on, then instead of getting 1 photon energy for the transition, then I now get 3 photon energies. And this was a big deal. It's a confirmation that the model of the angular momentum is actually generating results that are consistent with our concepts of angular momentum. That's what it's showing. That in fact our concept of angular momentum does actually bear out some reality when the experiment is done. And I'll take a pause here to think about it. Any questions on this? Yes.
So like the n equals 2, is that like a 2s orbital?
No, well, I chose the one I wanted to look at. right? So remember, if it's n equals 2, you can have L equals 0 or L equals 1, right? If it's in the L equals the 0, which is the S, then you would still only get the 10.2 eV electron. But it could go to the L equals 1. And if it goes to the L equals 1 with the field on, it can go to any 3 of these energy levels. And then when it comes back down, depending on which energy, if I do this and measure, 100 million photons that are decaying in a big bottle of gas or a glass tube, then I will see some of them make this transition, some make this, and then some make that transition. And then there'll be ones, as you said, that are in the 2s, but they're only going to get the 10.2. Okay? Now, you can also have transitions from the n equals 3 to the n equals 2. Okay? And there are some selection rules which say that you can only make certain transitions that are possible. And those transition rules say that the transition delta L must be equal to +1, -1, and that's it, right? Not 0. So you cannot have L equals 0 to L equals 0, not 0. So when the transition between levels occurs, it has to follow this rule. This is something that, I'm just telling you right now. I don't expect that you will need to know this, but the other rule is that delta M sub L has restrictions on them as well. It can be equal to +1, it can be equal to 0, or it can be equal to -1, but not 2, 3, 4, etc. Right? So these are called transitions. So they're selection rules for transitions. Selection rules. All right. It's something that comes out of quantum mechanics that we don't really have time to go into. But you cannot have a transition from L equals 0 to L equals 0. You can't have a transition from L equals 5 to L equals 3. Right? So I can't go from N equals 5. I can go from N equals 5 to N equals 2. But I can't go from L equals 4 to L equals 0. I can only go from L equals 4 to L equals 3 or L equals 4 to L equals 5. Right? It's just the transition rule that comes out of quantum mechanics. Probably won't affect us too much in this class, but I'm just mentioning it for completeness. Good question. Any other questions? Let's ask a question. Zeeman effect. Okay, makes sense? Front row? Yeah? Okay, good. All right. Okay, so that's the Zeeman effect. Yeah. We talked earlier about electron spin, and I want to revisit that a little bit because we're kind of on this topic of interactions of magnetic moments, the magnetic dipole moment, and its interaction in a magnetic field. By the way, this interaction is what electric motors work on. That the current applied, that if you apply a current through in a magnetic field, it will cause the loop to spin, and if it spins on this spindle out here, then it will continue to spin. If I reverse the direction of the current, by the way, you can't keep the current fixed. But the electric motor works on this principle of that it will cause a mechanical spinning due to the torque on the magnetic on the current loop. Okay, so anyway, I'm sure those of you that are going to deal with electric motors will see a lot more of that in the future. So the other point that is, I think, important is the concept of electron spin, and we've talked about this in relation to the Pauli exclusion principle, because we said that when we were counting how many different electron states you can have in an atom, that there was this other property called spin. And so in addition to having different values of N and L and M sub L, you can have two values of M sub S, which is called the spin angular momentum which can be equal to plus h bar over 2, or it can be equal to minus h bar over 2, right? These are two values of m sub s. So when we were counting the total number of states on a given shell, and by shell we have a given value in principal quantum number, then the number of states was equal to, we said, was equal to 2 times n squared. And that's how you exhaust all possible combinations of n, all possible combinations of L, m sub L, and m sub s for, so this is number of combinations. Combinations of L, m sub L for a given n value, right? So that's what we came up with before, and this factor 2 came up with the idea that in the atom, the electron can either have spin up or spin down. But what we haven't really talked about is what is up and what is down, and what does it mean? Obviously, it must be related to these two different values of m sub s, which is the z component of spin. So let's review what these what this definition is saying. First of all, the spin angular momentum, S, the spin, we call it the spin vector, is the magnitude of the spin angular momentum. And we're going to write this out more explicitly, but for right now I'm just giving you the quantum rules. That this is equal to the square root of S times S plus 1 times h bar. And the z component of angular momentum of spin can be equal to plus h bar over 2, or it can be equal to minus h bar over 2. Right? So when we take the z-axis, and by the way, we are going to design, the only way we can really choose a z-axis is to apply an external field to define the axis, which we can do, that by taking the magnetic field B, that the z component of the spin, the spin angular momentum, can either be spin up or it can be spin down, right? And this is S sub z. This is equal to plus h bar over 2, and this one is equal to minus h bar over 2. Okay? And that's really how you define spin up and spin down, is with respect to a external magnetic field. Now it turns out that because mu is in the opposite direction, right? Because for electrons, Q is negative. Then the magnetic dipole moment is going to be in the opposite direction. So I'm going to have to erase one of these here. So mu would be, this would be S. So let me label this as S. This is mu. Or if it's spin down, then mu is going to be positive, and this will be mu is pointing up, right? And the field B is in the middle. And by the way, this S is spin, right? This is not south and north. So S is spin. Okay. So everyone understand this is what spin up and spin down means, right? This is what it means. I mean, what is its quantized orientation in a magnetic field? It can only have two values of z component, a spin up or spin down. The magnitude does not change. The magnitude is fixed of electrons. So this is for electrons. And by the way, it's also true for all spin 1/2 particles. This part is true for electrons, but we now know that it's also true for protons as well. But the masses are different. But we'll come back to that in a little bit. But right now we're talking about electrons. Right? So the magnitude doesn't change, but the z component can be up or down, and we'll talk a little bit about that. Now, if I go to an electron in a hydrogen atom, you might suppose that if I take away these magnets, there's no magnetic field, right? Because we just went through that exercise. here's a magnetic field, and I take it away, then here's no magnetic field, and here's with magnetic field, right? No magnetic field with magnetic field. But what if there is a magnetic field intrinsic to the atom itself? Right? And how can that come about? Well, it can come about because if I were to sit on the electron, much as I would sit on the Earth with the sun moving around me, I would see a positively charged proton zipping around me at the same frequency as it sees me looping around it. Right? So if I sit in the electron, on the electron here, I see the sun rise every morning, right? The sun rises up, it moves across the sky, right? If the sun was charged, I would see a magnetic field due to the sun. That is because the sun is moving relative to me, right? The proton now is producing what we call a nuclear magnetic field, and let's see if I can find sure we get the right page for that. And I get a nuclear magnetic field. And now what I'm going to do is say, what if I am sitting in the middle as an electron, we'll say, right? But that's where I am. And I have a positive charge going around the opposite direction. So in my picture over here, I chose the proton that's going around, the electron is moving this way, going around this way. So if I'm sitting on the electron, I would see the proton moving in the opposite sense. So, I would see, the proton zipping around in this direction, and it has positive charge, right? So this now forms what I call a current loop. Current loop due to the proton. Everyone see that? I know it's a weird concept, but if you imagine that you were sitting on the electron, then you would see the proton going around you at some angular velocity. Just like we see the sun going around us at once every 24 hours. Right? We would see the proton. And because this proton is charged and it's moving relative to us, it generates a magnetic field. Right? So what is the magnetic field in the center of a current loop? Well, you have to go back to equations back in the Physics 273, and we can look that up, and we find that and I'm going to call this the nuclear current, right? Because the proton actually is part of the nucleus. If in fact, even if it's the only part of the nucleus. And so I'll call this the nuclear magnetic field, and that's equal to mu naught divided by 2r times I sub n, where I sub n is the nuclear current. And the nuclear current is given by the circulation charge, which of course, right, the charge Q sub p on this proton is equal to plus E, right? So the current is E divided by tau. Tau is the orbit time for the proton to move around the electron. And I can then do the same substitution as this equation over here, that tau is equal to 2 pi over omega. And so, let's see, tau is equal to 2 pi over omega. And so I get that this would be equal to E, did I get it right? Yes. Yeah. E over 2 pi times omega. Right? And this is the nuclear current. So I put that in up here, and I get that this is equal to mu naught times E divided by 4 pi r times omega. And now I've expressed the nuclear magnetic field in terms of the orbital frequency of the proton, which of course is the same as the orbital frequency of the electron, right? Because they're relative to each other. If the proton, we'll get back to that in a second. Okay, so this is the equation. Now, I can use my expression that, that angular momentum L of the electron, and this of course is the electron, or I'm sorry, I did this wrong. I'm sorry. Sure. One second. Yes, the orbital angular momentum. So this is going around at angular momentum velocity of omega. So it will have an angular momentum L, which is equal to m times r squared times omega. So r, of course, is the classical distance from between the electron and the proton. Describing it from that point now, and then I get that omega is equal to L divided by mr squared. And so putting in up here, this becomes mu naught times E divided by 4 pi m r cubed times L. Okay. And now what I have is that the angular momentum of the electron, or I should say it this way, this is a better way of saying it. The magnetic field of the proton is proportional to the angular momentum, proportional to the angular momentum of the electron. Of the electron, okay? So that's what this expression says, that the magnetic field, that an angular momentum of the electron will generate the observation of a nuclear magnetic field due to the proton going around it with opposite angular momentum, or with opposite velocity. Okay? Okay, now I have a magnetic field. And if I use for example, the right-hand rule, and I say, okay, then the magnetic field, if positive current is going this way in a current loop, the magnetic field must be, for example, into the board, right? So the magnetic field, what's in the board? Is X in or out? I can't remember.
It's in.
X is in, right? Okay, good. Thank you. X is in? X is in. Okay. Okay, so X is into the board. Okay, now when I talk about, now I'm going to put electrons. The electrons are going to be in their orbit going around, and I can either have an electron with its spin angular momentum pointed into the board, or I can have so now I need to go back. I'm sorry. Now I need to go back to the proton-centered picture. Right? So here's the proton, and here now is the orbit. And remember, there are 2 electrons in the 1s. So the 1s can hold 2 electrons. And for example, here. Since the magnetic field is, you said it was going into the board, right? Yeah. Since the magnetic field is going into the board, 1 electron can have its m sub s plus, m sub s equal to plus 1/2 h bar over 2. And this one will have m sub s equal to minus h bar over 2. This one will be anti-parallel to, or one will be anti-parallel. This one will be anti-parallel to anti-parallel to B, nuclear, and this one will be parallel to B, to the nuclear magnetic field. Right? So this gives me 2 different energy states. Right? The interaction potential is mu dot B. So mu is equal to minus mu Z times B nuclear. Right? This is the new interaction potential. And Now this mu sub z is due to the spin of the spin of the electron. And we're going to look at that a little more carefully in a minute. But that is due to the spin of the electron, not the orbital angular momentum. Okay? So we're going to get a new relationship, which we'll show in just a second, that for spin angular momentum, mu is equal to 1/2 E over m times mu sub z is equal to 1/2 E over m h bar times s sub z, or times, m sub s. I made a mistake here. This is m sub s h bar over 2. Okay? And this can either be, m sub s can be equal to plus 1/2, or m sub s can be equal to minus 1/2. And this is also written in vector form, that mu due to spin is equal to 1/2 E over m times s vector spin. Right? Whereas with orbital angular momentum, it's the same equation. It's just that orbital angular, that mu is proportional to the orbital angular momentum. So where do we have that here? Somewhere we had the magnetic dipole moment derived in terms of L. Right? Here we have mu, and this is for orbital. And this one is due to spin. Okay? Now, spin is another form of generating a magnetic moment, right? So we'll stop here for a question, but let me just draw one more picture up. The picture we're looking at for the electron is, here is a ball of charge of radius r that is spinning about the axis with some angular frequency omega. Okay? And it has a charge distribution, so it has an electric charge, which is E divided by 4/3 pi r cubed, and it has a mass density, which is the mass of the electron divided by 4/3 pi r cubed. Okay? But this charge density in every given sliver around here generates a current of charge, generates a loop of charge. So let's take a little sliver through the shell or through the slice of a sphere, right? Like this. Right? So everyone sees that now I've got a loop of current going on within the electron. Okay? It's a loop of current within the electron. So not only is the electron going around the proton, and it makes a current loop, but the electron is spinning on its own axis and has an intrinsic current loop. Right? You understand that? There's two concepts of spinning charge going on here, or two concepts of current loops. There's the current loop of the electron going around the orbit of the proton, and there's the current loop of the charge of the electron rotating around its axis of rotation, its spin vector, S. S is the spin vector, right? They both generate a magnetic moment because they both are circulating charges. Okay? So I think I'm probably not going to go through the whole derivation, but the derivation that I was headed towards is that the magnetic moment mu looks very much the same as the equation when we did it for orbital angular momentum. Okay? And this was given by E over m times the spin vector. Now, this can be derived. This equation can be derived from this picture. Just as we derived the same equation here for the orbital angular momentum. The coefficient is almost, well, and this is the way I've written it, it's the same. Now I got to tell you that there's a modification. That's not quite the truth, because people studied this and there is, and by the way, so mu sub z, let me put this down, mu sub z is equal to 1/2 E over M times h bar over 2, right? Because h bar over 2 is the z component of spin. But there's another factor which is called the anomalous g factor, and it is actually a factor of 2. So I'm going to put in here, sometimes it's called g, and for electrons, g is equal to 2. For protons, it's equal to 2.8. For neutrons, they're all different. The point is that the classical picture that is used to derive this equation does not actually work in the case, but it's almost the same. It just has a factor of 2 that's different. And a quantum picture is not going to lead to the same result. So the answer is we have to multiply this by 2. And mu sub z can be equal to plus or minus E over 2m times h bar over 2. Times h bar, I'm sorry, E over m. Plus or minus E over m times h bar. So this is called the anomalous g factor. It's actually a correction factor, right? This is called the correction factor to the classical picture. Correction factor. Relating, so it's relating mu equal to I times the area, pi r squared, right? To the angular momentum, L, equal to m r squared omega. And they are proportional, but the proportionality constant is not quite right, so we have this correction factor, which is g equals 2. Okay, now, not sure you need to know all that detail, but it is important because if you're going to add another quantum number called spin, and you're going to call it up and down, you need to know what up and down means. At least I do. Otherwise, it doesn't make any sense. Right? Yeah, do you have a question there?
Wouldn't it still be 1/2 EM h bar, seeing as the factor?
Yes, you're right. So I missed something. Yes, thank you. Yes, correct. Yep. I did. I thought something was off. I couldn't find it from up here. Okay. So now that's what it means. Okay. So what are the? What is the physical evidence that that this in fact is a true concept and picture? So now what we're going to do is just like we went here, right? We looked at n equals 2 to n equals 1, and we did field off, and then we did field on. Now it turns out the field is always on. It's just not as big as this one is, or it's not. This is an external field, right? But now there's a field that's on all the time because the nuclear charge is always rotating around the electron. Right? So now I'm going to consider a picture where I look at this. At the n equals 2, let's now look at another condition, from n equals 2, and we'll look at hydrogen, right? So we'll still look at hydrogen. And I'm going to do n equals 2, and I'm going to do n equals 3. Right? Well, okay, let's see. I now have 2 possibilities for mu sub z, and I know that the interaction potential U is equal to minus mu dot b, right? So let's just call this mu z times b. Minus is equal to minus mu z times b. But mu z can have two different values. One for spin up and one for spin down. So again, I'm going to incorporate the negative sign. So this will be E over mu, mu is equal to E over 2m times h bar. And B is the external magnetic field B right here. And I have one value for spin up, and I have another value which is for spin down. So I have U, which is minus E over 2m, h bar, oh, did I put the F times B, for spin down. Okay? So now what happens is that in the n equals 2 or the n equals 3 level, and I'm going to look at particular cases, one in which I'm going, this is L equals 1, and this is an L equals 2 trend over here, that in the L equals 2 shell, as in any other shell where L is not equal to 0, I'm going to get two energy levels here, one for spin up and one for spin down. And over here at n equals 2 and L equals 1, so this is L equals 1, and I can draw, I can draw divider lines here so you can get a feel for what I'm doing. And for the n equals 2 case, then I can have, these are also going to get split into spin up and spin down. So this will be for spin up, and this one is going to be for spin down. And similarly here, right? I got one there. But I have to have delta L not equal to 0, so I'm going from L equals 2 to L equals 1. I've chosen to go from n equals 3 to n equals 2. So what happens now is that previously I've had a transition in which n equals 3 to n equals 2 would have given an energy of 1.88 eV. Now, how did I get that? Okay, well, we just said n equals 2 is at minus 3.4 eV in hydrogen. If I put n equals 3, I forgot the exact number, but I think it's 1.54. The negative sign. And the difference of those two, I believe, if I did this right, somebody can do the math for me, is about 1.88. Okay? So this is going to be the energy difference that I would expect if there was no magnetic field due to the nucleus at all. If there is a magnetic field due to the nucleus, then I should see two more energy levels if a electron spin is real, and I should be able to calculate and predict what the energy levels are for those transitions. And in particular, I'm going to find that there's a transition from this one down to here. There's one transition. I can get a transition from this one down to here. That will give me another energy transition. And I can get a transition from this one down to here. That will give me a third energy transition. By the way, these energy differences are not the same. So don't get that confused. This energy difference is not the same as that energy difference. Right? Now, the point is that experimentally, that if I actually had 1.88 eV, I would expect to see 1. And so what happens now is that instead of seeing one peak that looks something like this, what I now see are there are three peaks there that look something like. And this, of course, is the photon energy, the energy of the photon on this scale. And we said that the middle here would be 1.88, if I've done this correctly, and I hope I have, it looks like I have. Then this would be the transition from a 3D to a 2p transition for the electron. Right? And in fact, I see three peaks. Right? And we can calculate the spacing between them, and we can calculate what the constants are that give the spacing. But the point is that the electron spin I should say electron spin. Let's put it this way: electron spin interaction with the nucleus interaction with the proton field with the proton B field, with the proton field, was confirmed. So this gave a reasonable, viable belief and interpretation that electron spin is a real property, and that electron spin is actually occurring in nature and isn't just something that we kind of can make a conjecture about make some unobservable predictions about. They actually bear fruit. They actually bear out that in fact this is what happens. Okay, make sense? Yeah. Okay, good. So that is the story of electron spin. There's one more brief topic that I will point out to finish this chapter, and that is called the Moseley effect. And the Moseley effect. So we just did the Zeeman effect. The Moseley effect was studied to confirm the electron shell model and the charge of the nucleus and the charge of nucleus. And the way this was done was to consider interactions that would show this. But the basic idea was that if we now go back to our picture of the atom, and now I'm going to assume that I have a nucleus or an atom with Z electrons, or Z protons. So the nuclear charge is Z times E, right? And there are different orbitals of electrons going around, right? Such as this, right? And we can now, let's suppose further, that we expose this system of atoms, or atoms in a gas, if you have to have that, to a stream of electrons that are zipping across from, let's say, the cathode to the anode of a device. And so if I have electrons that are going across here, then they can do a number of things. Well, first of all, what they can certainly do is, this is what we call an external electron, right? External electron. It can knock out it can knock out any electron in any orbit, right? And typically, if they knock out electrons in the outer orbit, then you knock out a valence electron. We talked about that with the photoelectric effect, and nothing really happens too dramatically after that, right? But now, let's suppose that I knock out one of the electrons in the inner orbit, right here. So now what happens is that I remove this electron has now been ejected out. And this is from n equals 1. And by the way, for historical reasons, just like we have SPDF for the angular momentum, we have KLMN for the n value. So this is called, the n equals 1 is called the K shell. The n equals 2 is called the L shell. The n equals 3 is called the M shell. Okay? So different notations, same physics. N equals 2, n equals 3. All right? Okay. So now what we can do is what happens when this electron has been knocked out. Well, now, because of the Pauli exclusion principle, this one is no longer here, and I can get a transition from n equals 2 down to n equals 1. Right? And that is going to give off a photon of a given energy. And this is going to be the energy of the photon that is given off. Right? Now, remember, if I have if you are an electron or you are a charge sitting here, looking here, then what you see for the nuclear charge is not just very high number Z, but it's actually Z minus 1. In other words, there are 2 electrons, and one of these electrons, well, there's 2 of them. There's only one now, right? The one electron after. So this one got knocked out. This one's still zipping around, but it shields the nucleus. It has a charge. So the effective Z is equal to Z minus 1 for electrons in n equals 1. Okay? So now what happens is that you remember from the energy formula that hc over lambda, which is the photon energy, is equal to the difference in the transition of the transitions from the transitions between different orbitals. So this becomes z squared times the Rydberg constant times 1 over 2 squared minus 1 over 1 squared. Or actually, the negative of that, I'm sorry. 1 over 1 squared minus 1 over 2 squared. Right? So now what happens is that I'm going to replace z with z minus 1. And I now can, this becomes 3/4 once I do that. And now the hc over lambda is equal to z minus 1 squared times the Rydberg constant times this another constant. So what Moseley did was that he plotted a graph and he went through most of the elements in the periodic table. And what he found was that for this particular transition, for n equals 2 to n equals 1, this transition from n equals 2 to n equals 1, and I plotted the square root of hc over lambda, which of course is the square root of the energy, versus z, he got a straight line. Right? And so he was able to do is to confirm that the charge present in the nucleus, was approximately equal to z minus 1 as a result of the transitions. So this transition from n equals 2 to n equals 1 was proportional to z minus 1. We do this for hydrogen, where z is equal to 1. So z equals 1 is for hydrogen. And we go all the way up to uranium, 92-235, for example. And you measure these energies. These energies are in the X-ray range. And it turns out that, for example, if I take z equal to 50, for example, then what I expect is that the photon energies for a z equals n equals 2 to an n equals 1 transition is not simply going to be equal to minus 13.6 minus 3.4, or I should say plus 3.4, no, plus 13.6 minus 3.4, but it's going to be times 2,500, which is 50 squared. This turns out to be of the order of, this is 10 of 25,000 electron volts, or 25 keV. These energies are called X-rays. And by observing X-rays at these energies, we can confirm that the nuclear charge is in fact given by this, because the transitions from n equals 2 to n equals 1 are consistent with a charge of the nucleus proportional to z squared. So it was able to show that the picture of the nucleus as being concentrated of a charge is accurate, because that's exactly what you would expect if you treated this as the energy levels of the Schrödinger equation modified for this excessive charge due to a large nucleus. So this would be hydrogen, and this would be uranium. So this Moseley effect was really, really important, and it establishes the confirmation that you can use these energy levels that we derived for the Schrödinger equation or for the Bohr model work exactly and predict the correct energies of the photons that you get by looking at these transitions from hydrogen up to uranium. It fit a straight line if you look at the energies for these transitions. Okay, any questions? If not, we will start. Oh, so chapter 40. Sorry, the next chapter is not in the book. So now what you do is you go to Blackboard start reading the pages I copied from Giancoli, and we will pick up there starting with the electron theory of conductors. So we'll do that on Thursday, okay?